My name is Ewa Borsuk, and I will show you a joint work with Paweł Błasiak, and that will be a causal reappraisal of the quantum freebox paradox. And our workshop is dedicated to quantum contextuality in quantum mechanics and beyond. So let me use that last structural causal models, causal DACs, and generated statistics. And when we talk about causal framework, generally speaking, it usually means that we have some physical phenomena that we want to describe. So ideally, we want to have some beautiful mathematical relations, some functional relations preferably, that would easily describe our phenomena. Then you would like to have some joint probability distribution that could describe what is really happening in an experiment. And in that approach, it is useful to use causal DAC as well, because it adds some quantitative relations to our description of an experiment of physical phenomena. So let me show you how I and my supervisor used it in a freebox paradox case. Firstly, I would like to go shortly through the freebox paradox, and I will do it in a nutshell, because I think most of you know it already. But the main idea of freebox paradox is presented on the right side of this slide. I hope you can see my cursor. I'm just trying to point it right now. But if you do, please let me know. Can you see when I point at things?
Yes,
or?
yes.
Okay, thank you. So firstly, we have some pre-selection. And that means that I have a particle and I want to have it in some desired initial state. And that is pre-selection. Then I will let my particle to go freely into one of three boxes, 1, 2, or 3. Then I will check where my particle is. And by the end of my experiment, I will make post-selection, which means that I will check once again if my particle is in the desired final state. So this experiment is a usual case of pre- and post-selection paradox. So where is the paradox in that story? You may ask. There's intermediate measurement that I call M2. And that measurement focuses on checking one of the boxes. And when I do such a measurement, I can find a particle in a box. Or maybe I won't find a particle in a box. That's pretty straightforward. For instance, if I check box 1, projectors of that procedure are described here. So once again, maybe I will find a particle, maybe I will not. And this brings me to the famous formulation of freebox paradox by Aharonov and Weidman, where they stated that whenever I have successful post-selection, whenever I try to look into box 1 or 2, I will always find a particle. I will find it with 100% chance. How is it possible? Does my particle just jumps into the box I'm trying to check? Maybe. But I will try to give you some possible explanations that was derived with the help of causal framework and causal DAGs. Okay, so here we are. What are possible explanations of free-box experiment? Which arrows are really necessary? Which arrows are really enough? In this part of my talk, I will give you two structures that can explain this paradox. The first one is a pure causal DAG. The second one is realist causal DAG. So let me show you what I mean by pure causal DAG. The pure causal DAG is created by just two simple assumptions. The first one is that I don't have any backward in time causation. So the timeline goes from left to the right. And all the arrows that you can see follows this logic. So I have no arrow that would incline some backward in time causation. The second assumption is that there is a free choice of the box measurement. So I can choose freely which box I will check. So there is no arrows going into C variable. Why C variable? Because C variable is a choice of a box. And that brings me to describing precisely variables. So as you can see, we have 4 variables on this DAG. The first one, C, is a choice of a box. M1 is result of checking a box, and M2 is result of post-selection. The fourth variable, lambda, is a hidden latent variable that describes all unmeasured influences that can disturb my measurements. It can be preparation of my system, for instance. But as you can see, these 4 variables are connected with blue and red arrows. The blue ones, I'm sure, because they are pretty straightforward. I can have some hidden unmeasured variable that will disturb both M1 measurement and M2 measurement. For sure, the choice of a box will influence the result of checking. But how about the 2 red arrows? Are they necessary? The question that I would like to ask all of you right now to answer in your head, if you can, is what is the role of a measurement disturbance in that scenario? Do I need an outcome dependence to explain the statistics? Or maybe I need just an arrow of parameter dependence, so from choice of a box to post-selection. How do you think? I will try to show you the results. I will show you the results in a few seconds. But firstly, let me go to realist causal DAG. We are in another possibility of realizing causal DAG for this experiment. The first one is pure causal DAG. The second one is realist causal DAG. And the second one adds just a simple, small assumption to the previous structure, and that is realism. By realism, I mean that it can be stated that the measurement reveals pre-existing properties of a particle, for instance, a position of a particle. So maybe someone believes that a position of a particle is something real, that it exists nevertheless of the measurement. So if a position is a real in that sense, then I can add it to my DAG. And I did it by variable v. And this variable just follows the logic of realism. This is just a position of a particle. In that scenario, we can say that M1 measurement, the measurement of checking the box, is just delta Kronecker of checking the box and position of a box. But how about red arrows? I will ask once again. Are they really necessary? Are they enough? On this slide, you can see the result of our work. There are a few possible solutions to three-box paradox. They differ in a way we describe the paradox, because there's a difference whether we look into full statistics of checking boxes or just the famous part with checking boxes 1 and 2. Because I need to tell you that in the original work of Aharonov and in most of papers concerning three-box experiment, the focus is stressed on checking boxes 1 and 2, because this famous 100% chance of finding a particle is only achieved with checking boxes 1 and 2. The third box is sometimes omitted. It doesn't give you this 100% chance, but it doesn't mean it is not important. In fact, I will try to convince you that this third box is very important, because no matter which causal structure I prefer, whether I prefer pure causal duck or realist causal duck, by the end of the day, I will get the same arrow from C to M2 if I look into full statistics. And how is it achieved? Firstly, let's go to the simplest version, and that is pure causal duck with checking just boxes 1 or 2. This duck does not really need any additional red arrows. It can be easily explained just by some hidden variable. So on the right side, you can see statistics of the experiment. And these statistics are reproduced by a structural causal model that I and Paweł Błasiak have created. And this model is represented on the causal duck that you see in the middle of this slide. And we really do not need any additional arrows. The whole phenomena can be explained by the disturbance of some unobserved variable. If I would like to check a realist approach to that paradox, the situation becomes more complicated. In the scenario of checking boxes 1 and 2, or 2, there are two possible arrows that I can choose. I can either want to have outcome dependence, so an arrow from M1 to M2, or another possibility, I can explain the statistics by adding an arrow from choice of a box to post-selection. Why is it so? The structural model is presented here, but it is just a version for this structure, because I will show you that this structure is repeated in the next cases. What is the meaning of these arrows. Why do I really need them? I need them on the basis of deseparation rules and on the basis of realist assumptions. Imagine for a second that I don't have these red arrows. They don't exist. And I have just blue ones that with which I want to explain my paradox. It is not possible. It is not possible in realist causal DAG because M1 is a collider. And that means that a path from V to C is blocked, which means that V and C should be independent. But on the other hand, they are not. They are not because M1 measurement reveals pre-existence properties of position of a box. They are bounded by Kronecker delta. So each time M1, the post-selections happens to be successful, V necessarily must be equal C. So there's a perfect correlation in that scenario. So we cannot have both. We cannot have realism and pure causal and realist causal DAG without additional arrow. So in that scenario, I will need to add at least one arrow, either an arrow from measurement 1 to measurement 2 to post-selection, or from choice of a box to post-selection. This brings me to another possibility, and that is looking into full statistics. So let's go back to pure causal DAG, to a DAG with no realism assumed. And let me check how this structure looks when I have the full statistics of checking boxes 1, 2, or 3. Can I explain it without additional arrows? I cannot. Which arrows I really need? Firstly, let me check a green arrow that goes from M1 to M2. This arrow was shown in the previous case, so maybe it will be helpful in this scenario as well. To do so, I will try, I ask you to use your imagination one more time and just erase this arrow for a second. Imagine that the red arrow does not exist, and we have just this structure with blue arrows and a green arrow. In that scenario, I will need to use instrumental inequalities, because a DAG that would be created without a red arrow is exactly the type of causal DAG that is described by instrumental inequalities. And these inequalities are shown in these four lines. And they are pretty straightforward. They just state that some of these conditional probabilities must be equal or less than 1. And this is really easy to check if the statistics follow this logic or not. And I can tell you that they do not. If we check, if we look into statistics of checking boxes 2 and 3, we will get 2/3 plus 4/9, and that equals to 10/9. And that is more than 1. So the arrow from M1 to M2 will not explain the statistics. It is not possible with just this arrow. So I will necessarily need another arrow from C to M2, because this is the last option I have, in fact, because adding any other arrow will break, for instance, no backward in time causation. So let me add an arrow from C to M2. Is it necessary and enough? It is. In fact, with help of that arrow, I do not need an arrow from M1 to M2 no more. I don't need it. And it is shown in the structural model, causal model that is listed here. The full statistics of this paradox, with checking boxes 1, 2, and 3, or 3, in pure causal structure can be explained by this causal DAC with parameter dependence, with an arrow going from choice of a box to post-selection. The last option that I want to show you is realist causal DAC in full statistics scenario. It is analogous to the previous one. The statistics follows the rule of just adding one arrow from choice of a box to post-selection. And that brings me to my summary. So me and Paweł Błasiak have presented two possible models that reproduce. We have created two possible models that reproduce the statistics of three-box experiment. There is a difference whether we look into full statistics or just the famous paradoxical part related to choice of measurement 1 or 2 box. There is a difference whether we look into pure causal structure and realist causal structure, and that is crucial because it impacts which measurement disturbance needs to be taken into account in description of the experiment. Thirdly, the famous part related to choices 1 or 2 does not really require any additional arrows in pure causal structure. So the whole story can be explained by a hidden or latent variable. And the last thing I want to tell you is the result that I think is the most interesting one, is that by the end of the day, it does not really matter whether I will check pure causal structure or realist causal structure. By the end of the day, when I look into full statistics, I will only need one additional arrow from choice of a box to post-selection. Thank you for your attention.
I admit I didn't follow a lot of what you were saying, but my impression is that you were using sort of classical ideas, classical notions of causality to investigate something which is quantum mechanical. Is that true? And isn't there a sort of quantum mechanical sort of explanation in terms of causes, which is possible in this case?
Okay, thank you for that question. My answer would be that, in my opinion, causal framework is a very general one. It really does not require things to be classical in a way. Even in epidemiology, causal structures were used broadly. This language is a mathematical language, and what I do with it is just my job. And our main goal is to use that language to try to explain some things in quantum mechanics. I think that is a broader goal, but I don't see a problem with using causal ducts or mathematics of causal ducts to explain a quantum paradox.
Isn't there a problem with, as I recall, Wood and Speckens concerned about, I forget just what, but they're getting into trouble with the causal model requiring, you know, some fine tuning and the like. At a stage where you can avoid such problems?
I think that it is interesting point. I will need to look into details of that remark. But from my perspective, causal ducts can explain many relations. For instance, the restriction that I do not wish to have backward in time causation. This is just my assumption. I can, in fact, imply it in a causal structure if I need to, if I want to. So I don't think there are much restrictions that would cause much trouble with describing quantum mechanics with it.
Thank you.